This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And
Myself,
price
and we
level
should be able to answer them fairly
what
promptly.
you have bought might
Now,
be lower
thing I wanted
or
to announce.
higher,
Yes,
depending
so
on what is
I think
the
that's all for
price level.
announcements. So today we're continuing on the theme of information retrieval. You recall that in the last lecture we talked about the very basics of the term
Just
documents
your
matrix,
expenditure.
how you
So
do,
the reason I say
how you
cost
can
is
use this
because
as an
is how much
index,
it's
how
going
you
to
can do
cost
efficient
you
lookup,
to
and
buy
today
these
we're
goods
going to
and
be moving on
services.
to
This
how
is the
you
amount
actually
it
get this to
costs.
work at scale.
You have
So
say for
how
example,
you can actually get these
1
technologies
plus I is equal to 100,
work
and price level P1
on very, very large
is 10.
collections and very, very
100
fast.
divided by
So
10
I'll hand
is
you
the
over to
amount
Matthias. He's
of goods and services,
a
the value
postdoc
of goods and
in the
services you
department.
have got,
He's been working on
because of the
information retrieval
price
for several
level
years
has increased.
very
And
knowledgeable about this.
if 1 is
So
equal to
I should
100
make
and
sure you don't talk, please.
price is $5, that means in period 0, without investing, you are able to
There's no-
purchase
Is that?
goods and services which
Okay.
has a market value of $20. That means inflation has eroded your purchasing power, and that's what real interest rate is going to tell you how
Is it
much
stopped?
it actually
Okay, so there's
values.
some strange. I reckon we're getting it from someone else's thing. I'll try the other. Oh, wait a sec. The last lecturer is standing outside with the thing on, I think.
Look,
So I'll fix that.
when we think about
Okay, you
real
set up.
GDP, we take price constant. Think about CPI, we have quantity constant.
I think you've got the thing still
Oh.
on.
Oh, I'm so sorry. Oh, I'm so sorry.
I wonder why there's noise coming through.
Oh.
It's not a problem.
So I'll be talking about information retrieval, right? Once I get the mic. Feel free to ask questions if you have any, right? Raise
Is
your
everyone
hand.
here at the back? No. Okay, so let's go. Wait a sec. I've got it muted. That's why. Okay. Do you want to put?
Do you want to do your announcement again?
Try this one. Okay. Everyone hear that okay? Okay, so that's better. So the announcement, we have Matthias here. He's going to be talking about information retrieval. He's an information retrieval expert, unlike me. And he'll be talking about how we do these, indexing and so forth at scale today. And there'll be a few more lectures coming up in the next one, and the one after that we'll be going through other things like query expansion and other topics around information retrieval. There's a homework. There are workshops running this week, so check on LMS for those details if you haven't already. Okay, I'll hand you over to Matthias. Thanks.
All right, can you hear me at the back? All right. So like Trevor said, we're going to look at doing information retrieval efficiently today in the next few lectures. So today we're going to look at inverted index compression, like how to make things small, and efficient inverted index query processing, right? So how do you make searching fast? Okay. So part of this is also going to be related to your homework, which you will see when you look at it, and I'll mention that briefly as well. Okay, so the first 10, 15 minutes, we're going to look at inverted index compression, right? So we have some sort of a data structure. We want to make it smaller, right? Okay, so I'll give you a brief recap, right? So let me switch to the document camera. So this is generally what an inverted index looks like, right? So you probably have seen a version of this before. You have the different terms that occur in your text. And for each of these terms, you store something called a postings list. Previously, this was more like a tuple of, for example, 1 and a floating point number, right? So document 1 has a score, has a TF-IDF component of 1.2 for this term. But in practice, that's not actually what you do. So in practice, you have these lists, 2 lists that you store for each term. One is called you store the document identifiers where that term occurs in, right? So for example, term and occurs in documents 1, 6, 7, 8, 9, and 12, okay? And the second information you store is how often does the term occur in that document, right? So that's usually called the term frequency. So in document 1, and occurs once. In document 6, and occurs twice, right? So and using these 2 information, you can compute TF-IDF and similar similarity metrics on the fly, right? So you don't store the floating point number because it turns out it's very difficult to store these things compactly. But if you store integers, you can do things like integer compression to make the index much, much smaller, okay? So these are called postings lists. So you have a list of document identifiers, which are increasing, right? So these numbers here are always increasing, right? And you have a list of frequencies which tend to be very small, right? So you have lots of small numbers for the frequencies. Okay, so this is what we are looking at storing and accessing in this lecture, okay? So back to the slides. Any questions so far? Okay, right, so this is an inverted index. You probably have seen something similar before, and now we're going to look at how do you make this smaller and how do you access it efficiently, okay? So to give you some motivation why that is actually important, so there's a test data set that I use in my research, and it has 25 million documents, right, which on a web scale is not a lot, right? So 25 million web pages. And it turns out if you process that, you get 35 million different terms, okay? So you have 35 million different of these different lists here, right? And in total, right, you have 6 billion postings, yeah?
Can you go back one slide?
Yeah.
Using lists there is indicative of the type of structure you will use?
Yes. Yeah, right. So these are called postings lists because they are lists of integers, right? And we'll look at how to store these lists efficiently and access them in the future, in the next few slides. Okay, so for a typical index of 25 million documents, which is not a lot in terms of web scale, but in terms of like what you would use these things for is actually quite a lot. You have 35 million different terms, right? 35 million different lists and 6 billion postings, right? So that refers to the number of different integers you have. If you count all the different numbers you store, right? You get roughly 6 billion, okay? So if you store them uncompressed using like 32 bits per integer, you need 32 gigabytes of RAM or disk space, okay? And today, in practice, a lot of these search indexes are stored in memory, right? So Google or Amazon and Facebook, they have lots of machines where all these inverted indexes are stored in RAM, so you can efficiently answer search queries, right? And 32 gigabytes is a lot of RAM, right? So we're going to look at how do you make this smaller, right? While still being to access these things efficiently, okay? In fact, we're going to look at, reducing the space to 5 gigabytes, right? So today we're going to look at a method that reduces the space from 32 gigabytes to 5 gigabytes, or 6 gigabytes. And this can really lead to lots of space and monetary savings, right? So if you just save 5%, right, and you have 1,000 machines, you can turn off 50 of them. Right, so even if you just save a little bit in terms of scale, that can mean a lot of cost savings, right? That's why companies try to be as efficient as possible when it comes to indexing, okay? So, like I said, the benefits of index compression, what we're going to talk about is you want to reduce the space usage, right? You want to keep more of the things you have to access in main memory, so you don't have to go to disk, which is slow. And if you have things in memory, you can process queries faster, right? And we're all about speed, right, when it comes to these things, which I'll talk about in a minute. So a state-of-the-art index, right, so you have 420 gigabytes of data, which is our 25 million documents, and if you use a state-of-the-art methods, you can compress it down to 5 gigabytes. Okay, so you can have an index that's 5 gigabytes in size, and you can use that to search 420 gigabytes of data. Right? And we can reduce our 32 gigabytes that we need in our uncompressed form to 5 gigabytes, which is 700% space reduction. Right? That's a lot. It can save us a lot of money. And we'll talk about a few techniques that you can use to do these things today. Okay? So I'll briefly talk a little bit about the principle behind data compression. So the compressibility of a data set depends on how much information is stored in the data set. Okay? So this is what we usually call the information content. And you can quantify that using a metric called entropy. Okay? So I'm not really going to go into the formula, right? It's on the slide. What's interesting about this metric is that it gives you a bits metric, right? So you have a text and you compute this metric, it gives you a number. For example, for this text here, abracadabra, compute the entropy using this formula, and it gives you a number 2.04 bits, okay? And that number represents the average number of bits you need to encode each of the symbols in your text. And it gives you a lower bound how good any compressor can compress this text. Okay? So it's like a metric that helps you quantify how well you can compress things. And intuitively, if you look at the formula, I'm not going to go into it. It turns out you're trying to spend less bits to represent symbols that occur often. Okay? So, for example, in this example, the symbol A occurs 5 times. So in your representation, in your compression algorithm, you want to spend less bits to represent the A's. Okay? So that's kind of the intuition, what you're trying to do when you do data compression, right? If things occur a lot, you want to spend less bits representing them. Okay? And we're going to use this principle to compress these postings lists that I talked about before. Okay? All right. So postings list compression, right? This is how you make the inverted index small. And we're trying to do 3 different things. We want to minimize the storage cost, right? We are going to reduce it from 32 gigabytes to something much smaller. We still want to be able to access it efficiently, right? We can make it very small, but if we can't access it efficiently, it's kind of useless, right? So we still want to be able to access it efficiently. And the last point I'll come to a little bit later, I want to perform this operation called GEQ. So we want to be able to essentially seek in our list of integers, right? So if you have a sorted list of integers, you're trying to seek to a specific one, right? I'll tell you more about this operation in a minute. So instead of just sequentially accessing this data, we want to be able to jump to somewhere in this list efficiently as well, which we'll need for efficient query processing. So I'll talk about that towards the end of the lecture. Okay. So I talked about postings lists, right? You have 2 different kind of lists. One that stores the frequencies of how often things occur, which are generally lots of small numbers, right? And then you have these other lists where you write down the document identifiers, right? Which documents does this term occur in, right? So in turn, you can sort this list, right? There's an increasing sequence of numbers, right? But these numbers can be very large. If you have capital N documents, right, you potentially need n log n bits to represent this number, right? So a trick, what you can do is, instead of storing the numbers explicitly, you store the gaps between them, okay? So in this example here, right, these are the document identifiers that the term the occurs in, 25, 26, 29, and so on, right? The is a very frequent English term, so it occurs in almost every document, right? So these numbers can become very large, right, if you have 25 million documents. However, if you store the gaps between the document identifiers, you get lots of small numbers, right? So the first number is 25, but instead of 26, you store 1, right? Because the gap between the first and the second is 1, right? So now we have transformed our sequence of potentially lots of big numbers to a sequence of small numbers, okay? So now we have 2 lists of numbers, frequencies that are generally very small, and we have these gaps that are generally very small. Okay? So if you think back of this, if you look back to this entropy slide, right? We're trying to spend less bits on things that occur often, right? So now we talked about how we can transform these postings lists into lots of small numbers, right? So now we are looking for a mechanism to represent small numbers efficiently, right? We are okay with spending some more bits on large numbers because they don't occur very often, but we want to spend less bits on small numbers, okay? So one very simple algorithm to do this, which you will also have to use in your assignment, is called variable byte compression. And the idea is, instead of using 32 bits for each, or 64 bits for each integer that you want to store, right? You store a variable number of bytes depending on how large the number is, okay? So what you're going to do is you're going to take your bit representation of your number and you're going to split it into 7-bit chunks, okay? And then you store these 7-bit chunks into bytes. So a byte has a 7-bit payload and 1 bit of indicators, which I'll give you an example in a minute, where you can then store, hey, is this number finished or not, right? I'll go through an example in a minute and I'll show you the algorithms. But the idea is, if your number is small, we only need 1 byte. If you have a little bit bigger numbers, right, from 128 to 16,000, we need 2 bytes, and so on, right? So if we have lots of small numbers, we only need 1 byte per number instead of 32 bits or 4 bytes, right? So we can save space. Okay, so we're going to have a variable byte representation for numbers. That's why it's called variable byte compression. Okay? So I'll give you one example. Let me go back to the document camera. Okay, so let's say we have this number here. So the way vbyte works, so variable byte compression works, is you want to split this thing up into 7-bit chunks, okay? So to determine how many bytes this number needs, you take the bit representation of this number, right, which I've written down here, and you split it into 7-bit chunks, right? 7, 7, and there's a bunch of bits up here, right? So you need 3 bytes, right? And the payloads for these bytes are, for right, this guy here, 0, 0, 0, 1, 1, 1, 0. This guy here, 0, 1, 0, 0, 0, 1, 0, and this guy here, 1, 1, 1, 1, 1, 0, 0. All right, so these are the 7-bit payloads that you need to represent this number. Okay? So how does it work? Okay, let's go back to the slides. All right, so this is what I just showed you on the slides. You need 3 bytes to represent this number. And how do we do it? So the first thing we do, we have to extract the lower 7 bits, right? So what we do is we take this number and divide it by 128, right, which gives us the lower 7 bits, right? And then we get our bit pattern here, right? Which is this guy. Then we discard the next 7 bits. How do you think we can discard the lowest 7 bits in a number? Right, we want to modify it somehow. And the way you do this is you divide it by 128, right? Which is equivalent to shifting your number by 7 to the right. Right, so our number has become smaller now, right? We went from our initial number to this number here, And this is the number we would write out to our byte stream. And now we do the same thing again, right? We have our smaller number. We extract the lowest 7 bits by doing mod 128. We get our next payload, right? This one. And then we keep going, right? Until we don't have anything left. So towards the end, we have a number that's smaller than 128, meaning we can represent it in our last 7-bit payload. And then what we do is we set the top bit to 1. Okay? What does that mean? All right, so our payload has a 1 at the top, which is an indicator saying, hey, this number is done. Okay? So we write these 3 bytes out to our byte stream, which represents this number. So if I go back to the previous slide. All right, so you have our payload, the payload here, and you have an indicator bit at the top that tells you, hey, this number is done or it's not. All right? A number that needs 2 bytes, you have 1 byte that has an indicator bit of 0 at the front, saying, hey, you need to do one more, you need to look at 1 more byte. And now we have our 1 bit here, right? Or if we have a number that's small, we just have a byte that has top bit set to 1. Okay? So very simple algorithm. And you will have to implement this in your assignment. And this is the pseudocode. So the encoding part is essentially what we have done on the slide. While the number is larger than 128, we mod 128 to extract our payload, and we shift it to the right. Okay? And the decoding part is a little bit more complicated. I'm not going to go into it, but that's how it works, right? So you can reconstruct the original number from this byte sequence that you're writing. Any questions so far? Yeah?
So you can still, when we have bytes, we've got like 3 bytes. And then the cleaning terms for the first 2 bytes are 0, 0, and the last one is 1.
Yep.
So then anytime we have more than 1 byte, the other leading byte always have 0.
Yeah, right? So the nice thing about this representation is it's kind of self-explanatory, right? As long as the top bit is 0, you know that you have to read more, right? And then as soon as the top bit is 1, you know, okay, that now there's a number finished. I can return it, right? So that's quite nice. A lot of other algorithms don't have this property, right? But here you just look at the top bit. Am I done or not? Yep.
You're only storing the byte at the top bit that's 1.
No, you store all the bytes, right? But the top bit only tells you when to stop decoding or encoding.
How are you compressing the number if you're storing the same number of bytes?
Because for small numbers, we only need 1 byte. For a number that's a little bit bigger, we need 2 bytes, right? And for the example, right, we needed 3 bytes, right? It depends on this range where your number falls in. But we talked about that we now have a lot of small numbers that we have to compress, right? So we want to use only 1 byte for each of those. And sometimes we see a big one, and then we can use 2 bytes, for example. Right? That's where the compression comes from. We want to use a variable number of bytes, depending on how big the number is. Okay. I'm not going to go, there's more compression algorithms, which I'm not going to go into. So I'll give you a small slide. So this is a table from a paper, which I find very interesting, right? So there are lots of people have done work on this in this area on how to compress numbers efficiently. And I took this table from a paper, or partially, right? So an uncompressed representation might need 32 bits per integer, right? And you can decode 5.4 billion integers per second, right? It's very fast. And our vbyte thing that we just looked at, on average for a certain data set, needs 8.7 bits per integer. That means almost all the numbers we are trying to compress, right? This was an inverted index, only need 1 byte. Sometimes we need a little bit more, right? That's where the 0.7 comes from, but most of the time we only need 1 byte. However, the speed is a little bit slower, right? There are lots of people who have worked on getting different trade-offs, right? So for example, this guy here uses 11 bits per integer, but it's pretty fast, right? You can decode 2.3 billion integers per second, which is very fast. Right? So there's lots of different algorithms out there where people do this. And VBoid is not the best, but it's very easy to implement, and it's still reasonably efficient. Right? So if you're interested, you can read this paper. All right. So I want to talk about a few optimizations that people do, which we'll need later on in the lecture. So often what you do is you have a big list of numbers, right? Imagine you have the term V, and it occurs in 25 million documents, and you have to store a list of numbers that has 25 million entries. So you might not always want to decompress the whole thing to get one number, right? So what you generally do is you block up these lists into blocks of, say, 128 numbers, and then you can individually decompress certain blocks of this list. Right? And we'll see later in a little bit why that is useful. Okay? Often, right, if you have very long lists like V, you might want to use a bit vector to just indicate, is this term, is it 1 or 0, right? Then you would only need 1 bit to indicate if this number is in there, right? Which is much less than 8 bits. And I've mentioned this before, I think. A lot of work has been done to make these things faster, using fancy bit parallelism and so on, right? So there have been people working on making VByte much, much faster than what I talked about here, right? But it's a little bit too complicated. But a lot of these things I talk about here, there's just off-the-shelf packages that you can use to implement these things. All right? So blocking is an important property that we're going to use in a few minutes. And the second thing that I want to talk about is fast searching. Okay? So I mentioned that we are interested in this GEQ operation, right? One second. What is GEQ? Right? So this is my ugly list of numbers. Right? So let's say this is one of the terms you want to use in your search. And with GEQ, right, this GEQ of x, let's say, for example, GEQ of 17. So let's say you have this operation GEQ, which means greater or equal, which means tell me what's the number that's greater or equal to 17 in this list. Okay? So you want this to return 18, right? So you have a compressed list of numbers. You don't want to decompress everything, but you efficiently want to know, hey, what's the next larger number or that's greater or equal to 17, right? So it turns out this is a very important operation that you need to do fast searching. And an interesting thing that you can do is you can do this blocking, right? So imagine we store this list in blocks of 3, okay? And for each of the blocks, we store the largest number uncompressed, right? So we store 12, we store 23, and we store 57, okay? And now we can do binary search on these numbers here, right? To determine if our 17 is in this list, it has to be in the second block. And then we go and just decompress the second block and not the whole list. Does that make sense? So that's why blocking is useful, right? Oftentimes we want to just know if some number is in this list. So we block it up and we store some of the numbers uncompressed. And then we do binary search on these to efficiently determine, hey, this is the block where it has to be in. Let's decompress it and look in there if it's actually in there. Okay? So it turns out this is a very useful operation, and using a very simple trick, right, which is on the slide. You want to do blocking, you want to store some samples, and you want to do binary search over these uncompressed numbers, yep.
Could we just directly do a binary search? I mean, instead of dividing, taking the greatest of those blocks,
Yep.
and then performing a binary search to find that block?
Yeah, but then you would have to decompress log n blocks, right? So you want to see if there's a number in there. You don't know. So essentially, you have a string of bytes, right? So you would go to somewhere in the middle and decompress a number, right? So you have to do decompression to do the binary search, which is inefficient compared to just storing the uncompressed numbers and then doing one decompression, right? And if you have blocks of size 128, the space that you need for these uncompressed numbers is negligible, right? So it's very small. Okay, so fast searching is a very important operation. Yep.
When you compress file,
Yep.
the words which are represented by a number,
Yep.
are they stored in the same file or is it stored somewhere else?
In generally, everything is in memory, right? So we're talking about an in-memory index, right? In practice, most things are in memory these days, right? So there are more considerations when things live on file, right? And you have to do disk seeking and so on.
So that means there's no question of missing information in the data.
No. In generally, everything you have bytes in memory somewhere, and then you can do a random access where you want to go, right? And you store pointer, hey, this block is here, right? And there has been more work in the 90s where people would use these things on disk. But nowadays, most companies use them in memory. Okay? So you kind of have an idea how to compress these things efficiently now, right? We can make things much smaller by using V-byte compression. We can block things to search things efficiently. Okay? So now we're going to look at how to use this technique to do fast searching. Yep? Yep.
Or for the frequencies or for both?
Usually you do it for both, right? So you basically, let me just show you this. It's like an implementation detail, right? So usually you have your block of document IDs, and then next to it you store your block of frequencies. And for each of these numbers, you basically say, hey, this is where the documents start and this is where the frequencies start. So you have some sort of pointer telling you, hey, this is where you have to stop. This is where you have to start decompressing things if you want to decompress this block, right? So what I wrote here is a little bit simplified, right? But in implementation-wise, you have a big byte stream, and for each of these samples, you essentially store, this is where you have to start decompressing to decompress this block. And that's where the frequencies in the document IDs are. Okay? Any other questions? All right. So now we can compress things. Now, our index is small, and we want to do efficient querying. Okay? So you've probably seen BM25 before, right? It's a version of TF-IDF, a little bit more fancy. This is the IDF component, and this is the TF component, right? And you have some things like document length normalization in there. So this is used in practice. It's a little bit complicated, and I'm not really going to go into how it is computed, right? But it works, and soft tools like Lucene implement this, right? And it gives you reasonable results. So what happens if you compute BM25? So let's say you have a query with a different kind of number of terms. For example, let's say you have everything uncompressed ready to go, and you want to compute this BM25 formula, right? There's logs in there, there's divisions in there, right? So you have to do some math, right? So it's not that cheap. But if you have a 4-term query, it still takes only 100 nanoseconds, right? It's very fast, right? 100 nanoseconds, that's like the cost of a memory access, right? So if you have everything available for a given document, computing BM25 for that document and a given query, it takes 100 nanoseconds, very efficient, right? However, what if you have 25 million documents, right? So each computation takes 100 nanoseconds, but you have to do it 25 million times in the worst case, right? So if you have lots of frequent terms, right, the occurs in almost every document, if you have to compute this BM25 formula for every document, right, and each thing, it takes 100 nanoseconds, which is very optimistic, it takes two and a half seconds. Right? And not a lot of people here, probably in this room, would want to wait for 2.5 seconds for their search query to come back, right? So that's not acceptable, right? We don't want to wait 2.5 seconds. So I'm going to skip over this. It turns out that lots of people have done research on that latency matters, right? If your search is slow, your users are going to go elsewhere, and you're going to lose money. Right? If you're interested, you can look at the slide, and there's some citations in there, right? So speed matters, all right? So there are a bunch of things you can do to make things faster, right? You can use more servers, right? But that makes your system more complex, right? If you have 1 million servers, that costs a lot of power, and making them interoperate makes things very complex. Another thing you can do is you can buy a faster server, right? But that just gets you that far, right? There's limits to how fast a server can be. So what we're going to look at now is how do you come up with a more clever algorithm to do the searching more efficiently, okay? So we're going to look at a software solution to this problem. And this is actually, what I'm going to talk about today is actually used in industry, right? Okay, so what we're interested in doing is something called top K document retrieval, right? So in practice, most of us are only interested in the top 10 documents, right? If you do a search on Google and it's not on the first page, you're not going to look at the second page, right? You're going to reformulate your query most of the time, right? So why would you want to evaluate your BM25 formula on all the documents that to create a whole ranking if you're only interested in the top 10, right? That's not smart. So what we want to do is we want to reformulate our problem that we are only interested in retrieving the top K highest scoring documents, right? We're not interested in a complete ranking anymore because that's what the user doesn't care. The user doesn't care about that, okay? So how are we trying to do that, right? So we're going to avoid scoring documents that we can somehow figure out will never be in our top K, all right? And we're going to fix our similarity metric. So let's say our index supports BM25. And we're going to pre-compute some stuff, which I'm going to talk about in the next few slides. And we're going to come up with a clever algorithm to use these things in addition to this blocking compression and GEQ operation that I just talked about to do fast searching, okay? So it's going to become a little bit tricky, but it's a cool algorithm. I think you should know how it works. Okay, so this is our BM25 formula again. And what's interesting about this is that computing this term is very efficient, right? Because it only depends on the number of different terms in the query. Right? I'm not going to go into what it means, but the problem with this term is the runtime complexity is O of n, right? Which means you probably potentially have to do this for every document in your text, in your document collection, and we want to avoid this, okay? So there's an algorithm, very famous by now, called WAND, proposed in 2003, and what we do is we process documents and keep track of the top K things that we are interested in. Okay, so we score documents and we keep track of the K highest scoring documents we have seen so far. And then we're going to use something called the maximum contribution, which is a little bit tricky, which I'll explain in a minute, to overestimate document scores. Okay. I'll explain that in a minute as well. And it turns out this helps us skip over documents that can never enter our top K. All right, so we can skip lots of stuff, which is what we are looking for. Okay, so we need this thing called the maximum contribution. So for each term in our document, right, for each of the lists that we're storing an additional floating point number, which represents the largest score any document in the collection has for a query that only contains that term. Okay? I'll give you an example in a minute. So this depends on the similarity measure, right? If we switch from TF-IDF to BM25, we have to recompute this. The good thing is we can compute this at construction time. So when you answer queries, you just have to look up a number, which is very efficient. And it turns out this helps us doing this overestimation, which helps us, in turn, to skip lots of documents that we don't have to evaluate. Okay? So it's very abstract, but I'm going to go through a long example now to explain to you what these things mean. Okay. So maximum contribution, what does that mean? For example, right, so I made up all of these numbers now, but I'll give you some intuition what the maximum contribution is, right? So the term fox here, right, so this is a sample query, the quick brown fox, and we're interested in the top K equals to 2 documents, right? That we are looking at the top 2 documents. So we have these maximum contributions, right? And what this means is, so we ran BM25 for the query that's just fox, okay? So imagine you evaluate the query that's just fox, and you evaluate it for all the documents. The only documents that have a positive score are these 4 documents, right? And one of these documents has a score of 7.1. All right, so Fox, in this example, Fox has a very high score because it has a very short list, right? So the IDF score is very, very, very high, right? It's an important term. And there's potentially one of the documents that only talks about foxes, so it has a high score. And we're not we don't care about which of these documents has a score of 7.1. We only care about that one of the documents, the highest score that we found is 7.1, okay? Does that make sense? So this is very important that you understand this, right? We are interested in, for each of the terms, if you just run the query by itself, right, with just that term, what's the highest score you get? That's what we call the maximum contribution. Okay? Okay. So the way WARN works is we process all the lists at the same time. Okay, so this is different from what you have to do in your homework. So what we do is we start at the start of each list, and we have these pointers, right, which tells us what's the current number we are looking at. Okay? And then what we do is we sort these lists. Okay? So we change the order of the rows here. All right? So now the top list points to the smallest document that we have not evaluated so far. Okay, so this is called document at a time processing because we look at all the documents from the smallest number to the largest number. Okay? So let's say we want to score document 2 now because it's the smallest we have not seen so far. And it turns out after we did our BM25 computation, it gets a score of 2. Okay? Then we move our pointers ahead, right? So we've evaluated document 2, so now these pointers move to 3 and 4. Okay? So the next thing we score is document 3, right? Gets a score of 0.5. So I'm making these scores up, right, to explain to you how the algorithm works. And we move the pointer ahead, right? We evaluated 3, so now it points to 7. We have to reorder the lists, right? Because the top list always has to point to the smallest document. Okay? So now we want to evaluate document 4. All right? So we can now decide, do we have to evaluate document 4? And what we do is, hey, document 4 is only in the list for brown, right? So, and we know one of these documents here has a score of 2.3, right? So potentially, it can be larger, can have a larger score than the smallest score we have in our heap so far, right? So we compare 2.3 to the smallest score we have recorded so far, and if it could potentially go in there, we have to evaluate it. Okay? So I'll give you another example where this is not the case. So we've evaluated 4. It did not have a score of 2.3. It had a score of 1.4. So it went in there. Okay, I'll skip ahead a little bit, right? So we just keep doing the same things, keep scoring things, and if it's larger, replace the thing in the heap. So now it's, something interesting happens, right? So now 6 is the smallest document that we have not evaluated yet, and we are thinking of evaluating it. Do we have to evaluate it? No, right? Why not? Because 6 only occurs in the list for the term quick, and the largest score any document that only contains quick has is 1.9, which is smaller than 2. So we know it can never be in our top 2, right? So we don't have to evaluate it. Does that make sense? So this is the main trick of the algorithm, right? We're going to use these maximum contributions to overestimate scores. Okay? Next question. Do we have to evaluate document 9? So what's different from the previous slide was that document 9 occurs in two terms, right? But the sum of the 2 maximum contributions is still less than this heap threshold, right? So even if document 9 is the highest scoring document for the term the, and it's the highest scoring document for the term quick, it still can't go in there, right? So we don't have to evaluate it, okay? So what's the next document that has to be evaluated? Yeah, 13, I'm not sure who said it, but right, we have to evaluate 13 next because the sum of these upper bounds, right, the next smallest document that has where the sum of the upper bounds is potentially larger than our heap threshold is document 13. Yep. It could be, right? We don't know currently, but it could be. So what's going to happen now is we're going to call this GEQ operation on the term quick and the, saying, hey, the next thing we're interested in is 13. Do you have 13? Right? But it turns out quick doesn't have 13, right? It has 14. So we do this GEQ operation. We know anything between 9 and 13 can't be in there. Go skip a bunch of stuff, right? And that's where the GEQ operation comes from, right? And now we reorder, right? And then we decide, hey, do we have to evaluate 13? And it turns out, yes, we have to, okay? So this is where the GEQ operation comes from. We can determine, hey, 13 is the next smallest document that can potentially go in there. Please forward your list a little bit, right? It turns out we can skip a lot of decompression of like things in these lists using this GEQ operation, okay? Okay, this is how the algorithm works, yeah?
How do we calculate that maximum contribution?
So the way you calculate it is, right, imagine you have, let's go back to the algorithm to the start. So the way you do is, for example, you want to compute the minimum contribution for the term fox, okay? So you run a query and you compute BM25 for a query that only is fox. Yeah. And then you get the largest scoring document is this number, okay? And the cool thing is you can do this at construction time. When you run queries, you don't have to do anything. You just look it up.
Okay, yeah.
All right? So if you can do something at construction time once, and it saves you doing millions of things later on when you answer queries, that's a very good thing, right? We want to pre-compute some stuff.
Does that take a lot of time?
Yeah, it takes time, but if you only have to do it once, that's fine, right?
Yeah.
All right? You want to be able to answer these queries efficiently, right? If you have to do something for a couple of hours in the background, that's okay, right? All right. So I'm not going to go into how the algorithm works because it's a little bit complicated and we're running out of time. So it turns out this works very well in practice. I'll show you an example in a minute. We use these maximum contributions to overestimate stuff. And we use a heap and this GEQ operation to do this, okay? So this, I took this from a paper of mine. And this shows you the percentage of documents that we have to evaluate. So for k equals to 10, right? So we're only interested in the top 10 documents, right? This is our 25 million document collection. We only, on average, we only have to evaluate 3.5% of the things that we otherwise have to evaluate, right? So we have a 97% reduction of the things we have to compute BN25 for, okay? And for 1,000, k is equal to 1,000, it's a little bit worse because you have to do more work, but it works as well, right? So it makes things much, much faster because we can skip a lot of stuff. So one last slide. So this is actually how this evaluation looks like. I'll spend 2 minutes explaining how this works. So 0% means all the pointers in our algorithm are at the start of the list, okay? So we have not looked at anything, right? 0% of all the things, documents have been processed. And 100% means we have all the pointers are towards the end of all the lists, right? We have looked at everything. Okay, and the blue line here is this threshold that we're comparing the number against, right? So this is the 6.3. And as the algorithm continues, right, this threshold increases and it gets harder and harder to get into our top K results, right? As you evaluate more things, it gets harder to get into our threshold. So it turns out we can skip more stuff. So each of these dots means we had to do an evaluation. And you can see as we process more things, we have to evaluate much less because our threshold becomes much higher, right? And this is how the algorithm works, right? The threshold of things that we are interested in becomes higher and higher. So towards the end, it's very hard for any of the documents to still be in our top K. That's what makes it efficient, okay? So you're not going to have to implement this, right? In your homework, you have to do something much simpler. But in practice, this is what you do, okay? And if you want to read it, the bottom one is the paper, okay? So it's a very cool algorithm. Any questions? Yeah?
You're doing an overestimate, right?
Yep.
With a lot of documents, maybe that's not going to be granular enough. By blocking
Yeah. So there's an extension to this algorithm called block maximum, where you store these maximums for each of the blocks that you want to decompress, you store another one of these scores. Yeah.
I'm just thinking about the calculation of that when you're, would it be doing the web while you're doing the web crawling?
Yeah.
Web crawling, you would just
Yeah.
calculate that again
Yeah.
and again.
I mean, in the end, it's just, for the term Fox, you just go through the list once,
Yeah.
right? It's not that.
But the list is always.
Yeah. But imagine you're doing.
If you Google and you're trying to use that.
Yeah. Still, but like you're doing this once, right? And then you answer billions of queries after, right? So.
And then you have to do it again though.
Yeah, the next time you rebuild it, you have to do it again. But
Like the new queries compared to the current list.
yeah. So you only do this in doing index constructions. When you answer queries, this number doesn't change, right?
Yeah, obviously, but aren't you like continuously constructing?
Yeah, right. So in the end, what you do in practice, once a day you rebuild everything, right? Yeah, or like eBay or whatever, right? Once a day they rebuild everything and then they compute these numbers, and then they can add some. So you lose a lot of money if your searches are slow, right?
Yeah.
So you're okay with spending some time computing these things if your users don't go away, all right?
Regarding the slide where we were just calculating the weights,
Yep.
we were not taking any weights which was the less value than the one.
Yep.
But in one slide there was 8.0 and 6.3. Then why we took 6.3?
Can you come around?
Okay, so why we took 6.3 even there is already 8.1?
Yeah.
Because this is the scores, right? We're looking for do we have to this score is higher than this one, right? So we are thinking about, hey, do I have to replace this guy, number 5, with potentially number 9? Right, we're not interested in replacing 7, we're interested in, do I have to replace 5? Right? Only if it's larger than this one, it can go in there. So we have to replace it, we have to compare it to the smaller one in the smallest one in the sequence.